Number 39 here is asking us to find the maximum and the minimum values of this particular rational function on a relatively tight interval here from 5 to 6. Now, the first thing I should say, they did not put an adjective right here in front of the word max or min. When they just say when they just say max or min, what they're talking about then, guys, is an absolute value. If they wanted a relative or a local extreme, they would have said that. Or they might have also said just find all extreme values there, but they didn't say that instead. So as I'm looking ahead at the solution right here, we should just be looking then on 39 for a maximum and a minimum value. Okay, that's what we're going for. This should be in your notes, plain as day, everybody, that a maximum or a minimum, an extreme value we call that, can only occur at critical points and at endpoints. Well, right here we've got endpoints at 5 and 6, but we need to find critical points. Critical points come from your derivative, dy dx, so we're going to have to get working on that. Looks like we're going to need the quotient rule here. The bottom is the denominator x minus 4 multiplied by the derivative of the top, which is just going to be a 2x. Probably didn't need that in parentheses, but that's okay. That's bottom times derivative of the top, minus the numerator, x squared plus 1 times the derivative of the denominator, which is just 1, all over the denominator, x minus 4 squared. So what's that going to do for us here, guys? We can simplify this. I'm going to distribute that 2x right there and get, I'm just going to write this right up here, 2x squared minus an 8x. The negative 1, the 1 isn't important, but I'm going to distribute the negative here and get a negative x squared and a minus 1. So trying to save some space here because these problems can get kind of long. Combining terms in the numerator, look in red, 2x squared minus x squared is a 1x squared, and then a minus 8x and a minus 1. All over our denominator, which is x minus 4 squared. Guys, on your last test, I'm still seeing some people writing this as x squared minus 8x plus 16. Don't do that, ever. Don't expand your denominator. There's no point in doing it. It actually hurts you and not helps you, and it's very possible you're going to make a mistake and lose a point there. Leave the denominator in factored form. Okay, there's our derivative. And now, guys, I'm glad we're doing this one together here. Critical points can occur in two ways: when your denominator equals 0 or when your denominator is undefined. And so I want to go ahead and write this out right here. Basically, guys, dy dx, your derivative, will equal 0. And let's think about this. If you have a quotient right here, the only way that quotient can ever equal 0 is if, that's not what I meant to write, is if your numerator is equal to 0. And then, I'm going to draw a line going right down right here, the only way that your derivative of a fraction, dy dx, can be undefined, that happens when your denominator is equal to 0. So with rational functions, these tend to work really well. I'm going to take my numerator, x squared minus 8x plus, sorry, that's a minus 1 right there. Let's not goof that up. And set that equal to 0, and we're going to try to solve this. Then, a little bit later, I'm going to let my denominator, x minus 4 quantity squared, equals 0, and I'm going to work on solving that. Okay, so where are we right now here, guys? Whoop. Well, we're off the page, Mr. Fontana. That's where we are. All right. This is a little bit of a pain, but okay. I've got a quadratic equation here on the left-hand side set equal to 0. And I would love to solve it by factoring, but I don't think there's two rational numbers, you guys, that multiply to -1 and add up to a -8. So you guys could solve this either. I suppose you could use your calculator, but that would kind of be cheating. My Algebra 2 kids would all use the quadratic formula. I like completing the square. So I'm going to do that and bring this 1 over here. I like completing the square when two things happen. When A is 1, and when b is even, and both of those happened here. So what do, guys? I take half of b, which is -4, square it and get 16, and I add that on the left, and I add it on the right. My left side is now x minus 4 quantity squared. My right side is now 17. I take the square root of both sides. X minus 4 is equal to plus or minus root 17, and then I add 4 there. Okay, so x is going to be 4 plus or minus the square root of 17. Now, what we have right there, guys, let's think about this. I don't know exactly what the square root of 17 is, but it's just a little bit more than 4, so I'm going to guess 4.1. What that tells me is that my x values here are probably 4 plus 4.1 would be approximately 8.1, and then 4 minus 4.1 would be negative 0.1. What's interesting about this problem, I saw it right away, they're only asking us to look here, guys, at x values that are in between 5 and 6. So even though I was kind of guessing as to the square root of 17, I know for a fact it's bigger than 4, which means that this number is bigger than 8, not in this domain right here, so throw it out. And I know that this number has to be negative, less than 0, also not in this domain, so I got to throw that one out too. Boy, that's weird. I kind of wonder if there wasn't a typo in this problem when they dealt with it right here. But anyway, okay, we did that work. We found two critical points that come from when the denominator equals 0, but neither of them is in our domain, so we had to discard them. And unfortunately, I think the exact same thing is going to happen on the second part of this problem. Let's look right here, guys, where our denominator would be equal to 0. That's where our derivative would be undefined. Well, this one, kind of hoping you guys can just stare at that and tell me the answer. Take the square root of both sides, add 4, you're going to get x equals 4 for a value for which your denominator would be 0, which would make your derivative undefined. But guess what, guys? 4 is also not in the domain from 5 to 6. So that means we have to throw this one out as well. That's kind of a weird problem in that regard. So let's be clear. Did we find critical points? Yes. This one right here, this one right here, and this one right here. These two values make your derivative 0. This value makes your derivative undefined. However, we only care about what's happening within this particular domain of values right here from 5 to 6. So back to the overall question here, find the max and the min values of this function on this interval. Those max and min values can only occur at critical points or endpoints. And even though we did find critical points, none of them were in the domain of this function from 5 to 6. So all we're going to do instead, you guys, let me zoom in a little bit more right here, is we're going to go ahead now and we're going to evaluate y at its left endpoint, which is 5, and then we're going to evaluate y at its right endpoint, which is 6. So a little anticlimactic after all that work. So, all right, guys, y was x squared plus 1 over x minus 4. Let me write that over here so I can see it. Y was equal to x squared, plus 1 over x minus 4. I can't remember anything. Yeah, x squared plus 1 over x minus 4. Okay, so I don't think this is going to be a whole lot of fun. Let's plug a 5 in there. 5 squared is 25, plus 1 is 26, all over 5 minus 4, which is 1. Hey, I can do that in my head. That y value is 26. Now, I have no way of knowing right now if that 26 is a maximum or a minimum until I compare it to the answer I'm going to get right here from y of 6. So putting a 6 in there, 36 plus 1 is 37. And down on the bottom, 6 minus 4 is 2. And I think I can do that too, guys. That is going to end up being an 18.5 right now. So what's going on right here, guys? The extreme value theorem, because I have a continuous function on a closed interval, guarantees me that I have an absolute max and an absolute min. The maximum is going to be the larger of these two values right here, guys. And so that one right here, this 26, is going to be our maximum. And this 18.5 right here is going to be our minimum. So for all that work here, guys, that's what we came up with for the answer here in problem number... This was 30, nope, I forgot. 39. That's what we were looking for. And I'm just checking the solutions manual right here. Maximum value of 26, minimum value of 8.5. So yeah, we still had to find all those critical points, but because they were not in the domain of the function, we had to throw those out, and we only ended up having to look at our endpoints. But I don't want you guys to misinterpret this. All of this work right here in the middle is absolutely necessary, and usually that'll give you at least one, if not 2 or 3 values that you need to check down there as well. All right, so that's number 39.